Don't forget to subscribe and ring that bell.
Glory, glory be. It is time for you and me to continue the 2008 AP Calculus AB practice exam. Thank you, College Board. All right, we are going to do free response question number 2. And woo, we get to use ourselves a graphing calculator for this one. Speaking of which, I do get people that ask me which calculator I use. I would highly suggest the TI-84 Plus CE, the color edition, because when you graph different functions, you have the different colors. It is beautiful, and the screen looks nicer than the regular TI-84 Pluses. The TI-84 Pluses look like garbage, the screen. It's like comparing Atari to, like, PlayStation 5. The graphics are just different. Okay, I have a boring yellow and gray set for my classroom, but in the description, I put links for all these different cool colors below. If you're in the market, check them out. I personally own one for my home use and personal use. It is that sweet, sweet mint green. Let's do some calculus. Number 2, let R and S in the figure above be defined as follows. R is the region in the first and second quadrants bounded by the graphs of y equals 3 minus x squared and y equals 2 to the x. S is the shaded region in the first quadrant bounded by the two graphs, the x-axis and the y-axis. So 2A is asking us to find the area of S. Okay, we're going to find the area of this gray shaded region. Now, even without a calculator, I should be able to tell which graph is 3 minus x squared and which graph is 2 to the x. However, you have a calculator and you can graph them both if you wish. All right, so in blue, this right here is 3 minus x squared. All right, 3 minus x squared. How do I know? It's a quadratic. The x squared term is negative, so it opens down. All right, and that is this one I'm circling in blue. 2 to the x, well, she's right here. Okay, that is 2 to the x. Okay, and that is the one I'm circling here in red. So if I want this gray shaded area, first of all, basic integration is area under the curve. So let's focus on this area right here under my two curves. Now, the great part is these curves never kind of occupy the same space. There is a point of intersection, but one is never over the other in terms of the area that I need to calculate. What do I mean? Well, let's go orange. This point of intersection right here, right? If I could come down here, okay, I need to figure out what this x value is. How come? Because in order to find s, I'm going to add all of this area that I'm horizontally, lining in red, and I'm going to add it to all this blue area with the horizontal lines in blue. And notice that the red shaded area is only under the red curve, and the blue shaded area is only under the blue curve. So I'm going to integrate my red curve, which is 2 to the x dx. All right, but I'm going to integrate that. Look at my x-axis here, from 0 to whatever x value I have here. Okay, that point of intersection. So from 0, and I'm going to put an x here, and I don't know what that is yet. I'm going to use a calculator for that. But I need to add that to my integration for my blue area. And here's the problem. My blue area, I'm integrating my blue curve, 3 minus x squared dx, all right? But I'm starting from this unknown x for my lower limit, and I'm going to this point right here, which is a 0 that I also am going to use a calculator to find out. All right, so I need to know this x value as well. Now it's time to grab that wonderful TI-84 plus CE. And, you know, I joke around, but really when you have two graphs like this, it's really nice to have different colors for different graphs. So let's turn on this bad boy. Let's go to y equals. And my blue graph, which is going to have the blue line, is 3 minus x squared. All right? And the red graph is my 2 raised to the x. Now, my window, you know what? Let's just graph this. I'll worry about the window afterward. There's my blue line, 3 minus x squared. And lo and behold, here's my 2 raised to the x just creeping along and shooting way up high. All right? Now, if I want to try and capture the same thing I have here, okay, I really don't have that. My y negatives aren't really there too much. I go up the y-axis a little bit, and only a little bit left and right. I mean, I want to see both x-intercepts on the blue. I'm going to zoom that area. We don't use this a lot. I'm going to pick zoom box. I use it a lot, but not a lot in the videos here. So I'm going to go, I don't know, I'm going to put my little spider dude right there and hit enter. And notice it's going to turn into this square. Now I'm just going to go up so I'm kind of like just a little bit above the top of the Y. I mean, I don't know, right there, and hit enter. And it's going to zoom in right on that box, and I love it. And that is a really, really good depiction of the image that we're given on our test. There we go. So if I take this and move this off to the side, how much further can I go? Let's continue. You can see I have a really good representation of it. And based on what I have here in orange and black written, this big mess here, I need to find this point right here of intersection, which looks like it might be 1. I don't know. But I also need to find this 0, because that's what I need for my bounds. So let's go ahead and use our calculator to find those two things. Second, trace, and first let's find that intersection point. Number 5. You can move my little spider dude close to the intersection. Doesn't have to be right on it. If you're anal and you want to be right at, there you go, right there. That's fine. I could be right there. I'm going to hit enter 3 times. 1, 2, 3. And if you look in the bottom left-hand side of that calculator LCD screen, it says x is 1. So right off the bat here, this x is going to be 1. Okay, that's my unknown. So if I look over to my integrals, the red integral now has an upper bounds of 1, and the blue integral has a lower bound of 1. I can do the red integral right now from 0 to 1, but I need to find the upper bound or upper limit of that blue integration, which is the 0, where 3 minus x squared crosses the x-axis. Again, and I'm talking about this point here. Again, I'm going to use my calculator, second trace, and I'm going to pick the 0 function this time. And I need to be to the left of it and hit enter. So I'm going to just go move to the right, anywhere, as long as I'm to the left of my 0. Right there, and I hit enter. Now I'm going to go to the right of the 0 and hit enter one more time. In case you did not know, that bottom left, it says x equals 1.7320508. That's the same thing as the square root of 3. Now, if you didn't know that, you could use this whole decimal. You will be fine. But I know that is the square root of 3. So now I have my upper limit for my blue integration. And right now, I'm going to put this in the calculator. I'm going to add them together. And that should give me my answer for the area of S. There was a lot to do, and it was mostly explanation, but hey, math 9 it. From 0 to 1 of 2 raised to the x, don't forget our dummy variable dx. I'm going to add that to the integration from 1 to the square root of 3. Again, you could have used that decimal, 1.7320508. It's fine. You'll come up with the same answer. But I like being a little bit more precise. Let's get rid of this little floaty arrow here. And that is of 3 minus x squared dx. I hit enter, and my answer is 2.2401. So we'll call that 2.240. Okay, that equals 2.240. That is the area of S. Ooh. 1B, volume. Find the volume of the solid generated when R is rotated about the horizontal line y equals 1. Okay, let's just recap, shall we? And let me get a good marker here. This right here. That right there is my 3 minus x squared. This curve right here, that's my 2 raised to the x, okay? They want, let's highlight this. Why not? They want R this time. Okay, they want R, but not only, they're not asking for the area of R. They want the volume of R as it's rotated around the horizontal line, y equals -1. So first, before we start drawing up more things on this graph, basic. For 2a, we had to know that integration was area under the curve. For 2b, you best know that if I want volume, I'm going to integrate area of the shape that I have, okay? So let's start to figure that out right now as we rotate that around the line y equals -1. We're going to get a circle. But be careful here. I'm going to extend this y-axis down. And let's call this line right here -1. Okay? Here's the line y equals -1. Y equals -1. Now, I've got to rotate my 2 to the x and my 3 minus x squared. And what do I mean? I'm going to end up with something that's, I don't know, right here, something that kind of curves up like this, and does this kind of mound thing like this, okay? And what's going to happen is as follows. This will be R when it's rotated, okay? We got this whole fancy thing right here. So first, let's take a look at the blue function, 3 minus x squared. I will do this, let's do this the black color. If I pick any points, let's pick up this point right here. And I rotate that. That will rotate to probably down here. You're going to get this thing, this disc. It's going to come down like this, come up like this. You're kind of going to get a circle. In the center of that circle is -1 on the y. Okay, so I'm gonna bring this out. I've got this circle, kind of looks like this. Okay, and the center of the circle is y equals -1. All right. Now, what's the radius? Why do I need the radius of the circle? Because the area of a circle is pi r squared. The only thing I need is the radius. Okay, so if I want to find this line from here to here, let's look at our graph. Here's the important thing, and I'm going to do this in orange. From my x-axis to my point, okay, that distance from here to here is 3 minus x squared. But notice, I go down another 1. I don't care that it's negative. Down meaning the direction. That's what the negative stands for. This distance is 1 unit. So I got to take my 3 minus x squared and add 1 to it. Okay? So my radius on the bigger circle is 3 minus x squared plus 1. I'm going to use a big R for the big radius. I know that's the area is R2. It's funky. So my radius for the big circle is 3 minus x squared plus 1. But we have another curve here. This isn't going to be a solid disc like a coin. It's going to be a disc with a hole in the middle of it. What do I mean? Let's get rid of this. 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 And we'll put this off to the side for now. We have an inner circle, which I will do. Oh my God, let's do this in gray. Okay. My red line, it's here. Okay. When I rotate, it's going to be here. I'm going to have a circle within the circle. Okay, so I'm going to draw that right here. I'm going to have the circle within the circle. Okay, that's going to be a hole. So I'm going to have like this washer, meaning I am going to, and I'm going to use that green highlighter again. I don't care. I got to find the area of all this. So it's the area of the big circle minus the area of the small circle. All right? So now I got to find the radius of the small circle. And again, okay, to the x-axis, the distance from my red line to the x-axis, well, that's my function, 2 to the x. But again, I need to add that distance of 1 for that gap. I got to add these two together. So the distance for the radius of the smaller circle is 2x plus 1. So this we'll call small r. That's also going to be the radius. So I take the area of the bigger circle minus the area of the smaller circle, and I integrate it. Okay? So what will that look like when I type it in the calculator? Integrate. Okay? I'm looking at my formula here. Pi is a constant I'm going to put on the outside. It's the bigger radius minus the smaller radius squared. So my bigger radius is 3 minus x squared plus 1, okay, minus, okay, minus, and really what I should do with this squared is I should write it like this, squared and squared. That's the appropriate way to do it. Okay, squared minus 2 to the x plus 1 squared, and I got my dx in there. Sorry, I ran out of space. Right? That's what I put in the calculator, and I hit enter. That's it. Okay? That integration will apply to both radiuses squared. The pi will apply to both radiuses squared. All right, so let's go ahead and make some math magic happen. On. Oh, my black marker's here. Gonna go here, delete all that. Turn it on. What you got? Pi first. Math 9. Oh, what are our bounds? We forgot our bounds. Oh, boy. So let's get rid of all this junk. Let's get rid of these circles, as pretty as they are. All right, well, here you go. I'm going to do this in a purple. This point of intersection, we already did this. That's 1. Okay, we did that on part 2a. So my upper bound is 1. I need to find this intersection point here. I need this x value. And again, I'm going to go to the calculator. I still have them in my graph. And I got to find this intersection point right here. That's going to be negative 1 point something. It's in between negative 1 and 2. But we can't just say negative 1 something when we calculate it. We actually need the value. Oh, my God. I am so far away from it. My spider dude has to work for this one. So I'm just going to hold this button down and get him closer to that intersection. A food for thought, if I would have hit enter 3 times with my spider dude closer to this, it would have given me this intersection. I need to put him closer to the intersection I want. 1, 2, 3. Oh my God, area bound. Graph, not quit. Graph, second trace. Did I pick, I picked a 0 instead of an intersection, didn't I? Enter 3 times. 1, 2, 3. Negative 1.637. We'll call that 637. Negative 1.637. So my lower bound, negative 1.637. Goodness, a lot of work going into this one. All right? So here we go. From negative 1.637 to 1, I'm going to integrate. 3 minus x squared plus 1, close that parenthesis. That's my big radius. That needs to be squared. Minus, parenthesis, the smaller radius, 2 raised to the x plus 1. Close that parenthesis off and square it. Dummy variable. 63.107. I will call that 63.107. So that is approximately 63.107. A lot of talking, a lot of explanation. There's things you need to know here. Volume is integration of area. You know that just because you're rotating it doesn't mean it's a solid circle. Could be a hole in the middle, which it is. And it's not just rotating around the x-axis. It's rotating around y equals -1. So there's additional distance in our radius, hence the +1 in each one. There was a lot going on there, but we got it. And you know what's cool? I like that little disc I drew. So cool. Last, certainly not least, probably the easiest one to do, even easier than 2A. The region R is the base of a solid. Okay. For this solid, each cross-section perpendicular to the x-axis. What does that mean? That means the solid, the base, will start here and be perpendicular to my x-axis. Okay, so it's going to be going vertically. All right? Is an isosceles right triangle. Okay, here we go. So if this were to come up, it would create a triangle. All right? And one of the legs is the base of the solid. So if this is an isosceles triangle, my legs are the same. Okay? This might be my hypotenuse. Right? Leg. This is a leg. All right? And let's not forget, this, my friends, is 3 minus x squared. And this, and yes, I'm going to call you friends, is 2 to the x. So what they're asking us to do is write, but don't evaluate an integral expression that gives you the volume of a solid. Oh, challenge me, will you? You're going to have me write it and not solve it, especially with a calculator? No, screw you, College Board. I'm kidding. I'm kidding. Anyways, let's go here. Again, basics. If I want the volume of a solid, that means I need to integrate the area. We said this for 2B. The area of a triangle is 1/2 base times height. In the case of our triangle, we have an isosceles right triangle. Here's our hypotenuse, leg. These are the same sides. So I can say my base and height is like leg times leg. So really, it's 1/2 times a leg squared. This is what we're integrating. So I'm going to integrate. Okay. 1/2 will go on the outside. I'm going to take the leg value, whatever it is. I might need a little bit more space there. Let's not be crass, people. And I've got to square it. I've got to take my leg and square it. So what is the leg? That's what I'm trying to find out. The leg goes from one to the other. The distance between that green highlighted line here is my upper function minus my lower function. So it is quite literally this point, 3 minus x squared, and I subtract 2 to the x. 3 minus x squared minus 2 to the x. Last, for 2B, last problem, I almost forgot the bounds. For this one, we're not going to. The bounds are exactly the same because it's still the same region R. It's going to go from negative 1.637 to 1. We are done. The easiest problem on free response question 2 was not A, was not B. It was C. We're done. You are going to nail this test. You are going to get a 5, no problem. And we're going to celebrate. I'm going to throw you a little party when you get a 5. I'm going to send you a cake, drinks, food. I hope you like chicken French or chicken parm because I love that stuff. I'm not sending you anything. But you know what you can do? You can like the video. You can make a comment. You can follow me. Because if you follow me, that's when you get notifications of when I put up future videos, like maybe free response question number 3. Have yourself a good day. I'll be seeing you later.
Don't forget to subscribe and ring that bell.